Welcome back in my today's session. Today I will discuss some important questions on force on electromagnetic field. So these questions already some we have discussed in the previous class, and there will be the recaps, and then we will start our new topic. So first question is, which is come in our mind, is the force on a moving charge. What do we mean by the force on a moving charge? Magnetic field can exert a force on the electric charge if it is moving. If the charge is stationary, it will not exert any force. So we can tell magnetic fields can exert a force on electric charge only if it is moving. And we can write the force as F is equal to QV cross B. The equations can be written as F QV cross B. What are this nomenclature is? The nomenclature is Q is the charge. What is the Q? Q is nothing but the charge. And V is the velocity and B is the magnetic field strength. V can be written as flux per unit area phi by A. V can be written as flux per unit area. And it always works in a perpendicular way. That it always acts in the perpendicular to the velocity. This is the direction of the force. It acts out of the plane and does not contribute any work done on the charge. And the direction of the force can be easily determined using the Fleming's right hand rule. Next important question is, explain the Lorentz force. Lorentz force, first we will give one example. Say we have a DC machine. So we have a north pole and south pole, and there are some lines of force. This is the stator part. Now we are keeping, I am using the another color for your is for this. So I am keeping one armature in the magnetic field. The current is flowing. So what will happen? Due to the magnetic field on the electrical conductor, there is one force due to the electric field, and according to the Coulomb's law, this is AP is equal to Q into E according to the Coulomb's law. And what is E? E is nothing but the field intensity. What is this? This is nothing but the field intensity. Now, so this is due to the electrical field. Now we will consider about the magnetic field, and we just came, if there is a moving charge is nothing but the current. The direction of the current is always opposite to the moving charge, opposite to the moving electrons. So we can write Fm is equal to V cross B. So if we consider this field, there are two types of field is basically present. One is the magnetic field, one is the electrical field, and total force is Fe plus Fm. What is Fe? Fe is Q into E, and what is Fm? Q V cross B. So if we take Q common, we can get E plus V cross B. Or we can, if we write it in the scalar form, it will be Q E plus VB sin theta. Q E plus VB sin theta if we take the scalar form. And always remember, the force is always, if while we are taking the right hand screw rule, we will take V and B, not B cross B. In the cross product, V cross B is minus of B cross B. So both are not equal. Next, what are the limitations of the moving charge in magnetic field? The limitations of the moving charge in the existing magnetic field: if the velocity of charge in the magnetic field is 0, then the force experiences 0. What that is means? We wrote F is equal to Q V cross B. Now, if the charge velocity is 0, What does it means? V is 0 means either it is a stationary charge. So in case of the stationary charge, or we can better to tell the static charge, the force equals to 0. If the velocity direction and the magnetic field directions are parallel, then, and we can also write Q VB sin theta. Now, if the velocity direction and the v direction both are parallel to each other, so theta is, in this case, theta is equal to 0 degree. Again, the force will be 0. So this is the, and again, if the, so these are the major two drawbacks of or limitations of the moving charge. If it is a static charge, there is no effect of the force, and if the velocity direction and the flux direction is also are parallel to each other, if the angle is 0 degree, then also force is 0. To say that moving charge in the experience, when the force has the velocity, and if the field is normal to the B, if theta is equal to 90 degree, if V and B both are 90 degree, then it will be the maximum. Why? Because the 90 degree sin 90, we know the sin 90 is always 1. So these are the, next is the another important question. Deduce the force on the current element due to the magnetic field. So first let us consider first we will consider a length L, and we will partition it. We will consider a long conductor whose length is L, and we will partition it in the small part, and it is dl. And we are also thinking the current through this each length is I. Current per I, ampere per meter. So what is the amount of current is this length? The length of current in this is I into dl. Now we know df is equal to dq v cross v. Or what is velocity? Velocity is nothing but the dl by dt, the length or the displacement by the time. And again, from the previous equation, we know dq is equal to rho v by dv. Rho v is nothing but the volume charge density, and it is equal to q by v. So we can write that the rho v is equal to rho v into dv is equal to dq. So we can put the value here, and we will get rho v dv v cross v. This is the another term. Again we know that the rho v is equal to j cross v, because the j is equal to rho v by v. Here this v is nothing, the small v is the volume and capital V is the velocity. This is the velocity, and we can call it as the drift velocity of the electrons. So we are getting that j is equal to rho v by v. So j cross v dv equal to I cross v dl. Why? Because j is nothing but the, what is j? Current density. J is equal to current per unit area. So we can write it as the I into I by A cross V, I by A cross V by dV. What is volume? Volume is nothing but the, what is volume? Volume is nothing but the area into length. So area will cancel out, and we can write I cross V dl. So df is equal to, we are getting df is equal to I cross V into dl, or we can write IB sin theta into dl. If we integrate the both side, what will happen? I is constant, B is constant, angle is constant. So F is equal to BIL sin theta, where L is the length of the wire. So here we can discuss about the current. Next one, write the expression for force due to parallel straight conductor. What is this? Say we have one H, we have two long parallel conductors and the distance between them is D. So according to the Ampere circuital law, H is equal to I by 2 pi d. H is equal to I by 2 pi d. So again we know the relation between H and mu. H is equal to, or B is equal to mu into H. So we can write B is equal to mu naught, H is equal to I1 by 2 pi d. So this is the equation of the B. Now we are coming to the main equation. The force on I1 due to I2, due to the current of I2 is equal to B I2 into L. Because we know F is equal to B I L, and as this is we are taking theta is equal to 90 degree, the maximum force. So it is F1 is equal to B I L, and due on I1 due to I2, so we can write B I2 L. What is B? B is nothing but the I1 by 2 pi d I2. So we are getting into L. I1 I2 by L by 2 pi d. Same thing, if we calculate the force on I2 due to I1, then again we will get mu naught I1 I2 L by 2 pi d. In the both case we are getting the same value. So force is equal to basically mu I1 I2 by 2 pi d into L. L is the D is the distance between these two, and what is L? L is nothing but the length. If the both currents are in the same directions, then there is the force is in the repelling force. If the currents are in the opposite direction, it is the attractive force. So what is F? F by L is equal to mu I1 I2 by 2 pi d. So this is the main equation, force per unit length for a two long conductor. Next question is, classify the magnetic potential. So what is magnetic potential? Magnetic potential is the property of the certain substances or phenomena Magnetic potential is the property of certain substances or phenomena that gives rise to the magnetic field. So magnetic potential can be divided into two parts. One is the scalar potential, one is the vector potential. Scalar potential is similar to our electrical potential, the work done to bring one unit north pole from infinity to the field. Vector potential is the special property of the magnetic field. So, as I told, magnetic scalar potential psi is a quantity in classical electromagnetism analogous to electric field. In electrical field, we got E is equal to minus grad V. We know E is equal to minus dV by dr. So, d by dr we can write by grad. So, minus grad V. So similarly, what is H? H is nothing but the minus grad Vm. What is Vm? Vm is nothing but the scalar magnetic potential. Now, if we take the cross product in the both side, what we will get? Cross grad dot H is equal to minus grad cross grad Vm. So we are getting grad cross H is equal to minus of grad cross grad Vm, as grad cross H is equal to 0. Again we know grad cross H is equal to J. So if we compare the both equations, we can get the current density is equal to 0 in the case of a scalar magnetic potential. What is the divergence of curl of a vector? What is the meaning of divergence of curl? Say A is a vector. We want to calculate the curl. Curl means grad cross A. If it is a single dimensional, so it is the del by del x cross A. If it is a two-dimensional, then del by del x plus del by del y. This is the grad cross A. If it is a three-dimensional, del by del x plus del by del y plus del by del z cross A. So this is for the Cartesian coordinate. Same thing we can write for the cylindrical and spherical. So if we take the divergence, what is the meaning of divergence? Grad dot product of grad cross A, and the value is always coming as 0. So the divergence of the curl of any vector, if we calculate it, we will get the value 0. So next one is the write the NEUMAN formula. NEUMAN formula about the inductance. So let us consider two circular coils brought as this is a circular coil and this is another circular coil, and we want to bring the two circular coil I1 current having I1 and I2, and we want to bring it nearer, and the separation is R between them. The areas are S1. What is S1? S1 is nothing but the 2 pi R1. S2 is nothing but the 2 pi R2. So we got the R1 and R2. So the magnetic flux due to the current I1 is B1 equals to grad cross A1. What is A1? A1 is nothing but the vector potential or magnetic vector potential. So vector magnetic potential, and what is the value of A1? A1 is the integration of mu I1 dl by 4 pi r. Hence the flux with the second coil due to I1, the flux in the second coil phi 2 1, flux of the second coil due to 1 is equal to B1 by B1 into ds2. So what is the total flux? Total flux phi is equal to integration of B1 into ds2. What is B1? B1 is nothing but the grad cross A1 into ds2. What is grad cross? What is A1? Integration of mu I1 dl1 by 4 pi r. So we can write grad cross A1 into ds2. Now we are applying the Stokes theorem. In the Stokes theorem, we know if we use the grad cross A ds, it will be the change in 1 unit. So it will be the ds will be changed in the lower unit s from surface integral to line integral. So surface integral is changing to the line integral, and it is coming A1 di2. And what is the A1? A1 we have discussed in the previous slide, mu I1 di1 by di2, dl1 by dl2 by 4 pi r. So the mutual inductance, we know what is the mutual inductance. Mutual inductance can be referred as the psi21 by I1. Inductance can be written as the flux per current. So if we write mutual inductance M21 is equal to double integration of mu I1 dL1 dL2 by 4 pi r, or L1 is the length of the circular coil and r is the distance between them. So we got this two equation. We got the two equation in the NEUMAN formula. M21 is equal to double integration of mu I1 by dl by dl2 by 4 pi r by I1. So I1 will cancel out. So we get mu dl1 dl2 by 4 pi r. If we want to calculate the Mi2, what is the meaning of M12? M12 means the mutual inductance of the first coil due to the of the second coil due to the first coil, and in this case we will get same value integration of mu I1. We will get mu dl1 dl2 by 4 pi r. You can see M12 and M21 both doesn't depend on the current value. So we can write M12 is equal to M21 in this case. According to the NEUMAN's formula, the mutual inductance of two circular coils are always equal. So this is known as the NEUMAN's formula. Give the expression for self-inductance for solenoid. So first, in the last class, we have discussed about the solenoid. So what is the solenoid? So for first, solenoid is a bar on which we are keeping the coil. So let us consider a solenoid as shown in the figure with length L, allowing the current I ampere is flowing in it. N is the number of turns. N is the number of turns per unit length. So N is equal to total number of turns N divided by L. So the magnetic field density inside the solenoid is B is equal to mu naught N into I. As we know, the H is equal to N into I, and B is equal to mu into H. So what is the total flux linkage? So total flux linkage is number of turns into the B, the flux density, and A. A is the cross-sectional area. And we got mu naught N. What is this? This is the N. Capital N is equal to N into L into I, and this is our B. So this is the B and the A. Sorry. NIL is the B into A, and again the N. So this is the formula. What is N? N is nothing but the capital N is equal to N into L. What is B? B is mu naught N into I, and then we are calculating the A. So if we write this, we will get mu naught N square L into I by A. And the self-inductance, as we discussed, that inductance is N phi by I, flux by I for the total number of turns N phi by I, and if we put the value, we will get the phi value is mu N square I by AL by I, current, and we are getting mu N square A by capital I. Give the expression for magnetic flux N turns if B and A are known. So already we have discussed about this. So we can write the magnetic flux phi is equal to NBA. N is the number of turns, B is the flux density, and A is the cross-sectional area. And we can also write N is equal to N into L, number of turns per meter per length. B is equal to mu naught N into I into A. So it is coming N square L I A. Next, define the magnetic dipole. Magnetic dipole is same as the electric dipole. Magnetic dipole is formed when two opposite magnetic charges are separated by them by L meter. So, what will happen in that case? They have the same field strength but in the opposite direction, and it will give a circular force. So we can write that the small m is equal to qm into L. The magnetic dipole's m is equal to qm into L, and L is the distance between the plus qm and minus qm, similar to the electric dipole. Write the expressions of the magnetic dipole moment. So what is the meaning of the dipole moment? Dipole moment means the force or torque needed to rotate something. So we can, again we are taking qm plus qm and minus qm. So we got the magnetic dipole m is equal to qm into L. L is the length. Let us consider a bar conducting. Now we are keeping one bar, and that is a current carrying loop. This is the current carrying loop, and its cross-sectional area is A, and the current is I Ampere. So what is the magnetic dipole moment? M is equal to I into A. I is the current, A is the magnetic dipole moment. So we can write QMI is equal to I into A. Define the magnetization. Define the magnetization. If there exists any conductor consisting of a number of dipole in its unit volume, then magnetic dipole moment per unit volume is called as the magnetization. So capital M magnetization we write by capital M. M is equal to small m by V. And small m we got qm into L. In the previous section we checked dipole is equal to qm by L. What is volume? Area by L. So we can write qm by A. The qm worsted per meter square. We can write worsted per meter square. Energy stored in an inductor. So when there is a inductor and capacitor is known for the storing of the energy. So let us, there is an inductor and the current di is flowing, and as a result there is a work done of dw. So what is the dw? dw is equals to the energy, and we know energy is equal to power into time. So what is the power? VI dt. VI dt. Now what is the V? V is equal to again L I di. L I di. This is our V, and this we are L. What is the voltage in an inductor? L di by dt. So in the place of V we are writing L di by dt into I into dt. So dt will cancel out. We will get dw is equal to L I di. If you take the integration in the both side, we will get L I square by 2. Again, L is equal to, we discussed previously, N phi by I, or we can write psi by I. So we can also write that the W is equal to, if we put the value, so what is the W? W equals to psi I. In the place of L, we are writing psi I by 2. What is psi? Psi is equal to n phi by I, and if we put the value, we will get W equals to psi square by 2L. Write the characteristics of the permanent magnet. Permanent magnet are one which readily available in the nature in the form of bar and horseshoe shapes. Either it is in the bar type or in the horseshoe type. Permanent magnet, irrespective of the supply, always exhibits the magnetic properties. It always exhibits the magnetic properties. Permanent magnet always develops a constant magnetic field. This is the strength of the permanent magnet measured in the terms of their cohesive force. A permanent magnet with a high cohesive force has the long life. Permanent magnet got the disadvantage of edging effect, as this is a natural thing. If the energy is more, it will always, due to the corrosion, it will become this is a disadvantage of the permanent magnet. So next important questions, what is the inductance is? The voltage across inductance means if there is a coil and if there is a rate of change of current, if there is a sudden change in the current, inductor always opposes the change of current. So the voltage of an inductor directly proportional to the rate of change of the electric current flowing through the inductor. We can write V is equal to L di by dt. What are inductance? Inductance is basically two types. One is called the self-inductance, another one is called the mutual inductance. What is this? Is we have already discussed the self-inductance. So we will discuss about the self-inductance of a toroid. What is a toroid? Toroid is a circular path where we can keep the coil. So this is a circular path. N turns is wounded in allowing the current I. Let R is the radius. R is the radius of the toroid. So therefore the self-inductance, so the magnetic flux density B is equal to mu naught N I by L. Already we know B is equal to, what is B? B is equal to mu into H, and H is equal to Ni by L. Actually H is equal to small n into L, and so small n into I, and small n is equal to capital N into I. So we are writing mu naught Ni by L, where L is equal to 2 pi R. So we can write B equals to mu naught N I. For the circle it is 2 pi R. So if we put the value, we can get L is equal to N square mu naught R square by 2R, where smaller is the, you can see here capital R. You can see here capital R the radius of the outer circle, and the small r is the inner circle radius. We have already discussed the energy stored in an inductor. Energy stored in two inductors if the medium is linear. If there are two inductors, from the NEUMAN's formula we can write M21 is equal to M12. So the total energy W is equal to half L1 I1 square plus half L2 I2 square plus minus M12 I1 I2. Plus minus depends on the direction of the inductor. So this is the inductors for the two inductors. So if you can see, if this is an inductor, this is the another inductor. For the coil 2 number of turns is N2 and the coil 1 number of turns is N1. So the total energy is half L1 I1 square plus half L2 I2 square plus minus M1 to I1 I2. So in our today's session, we have discussed about the force on a moving charge. Then we discussed about the force on an electric coil. Then the different types of magnetic potential. What is inductance? What is the property of the inductance? Then we have discussed about the inductance of a solenoid, inductance of a toroid, and we discussed about the properties of the magnetic field. So this is my today's class, and thank you.
Like, share and subscribe. Hit the bell icon for more updates.